Right at this moment, while you are reading these lines, something is happening in a small room in Pasadena that almost no one on Earth knows about. An engineer has just typed a long command of only a few dozen bytes. That command has just begun its journey of nearly 23 light hours through the dark void to reach a machine drifting in the darkness between the stars. When that command arrives, it will permanently shut off one ear that has been listening to the universe for 48 years and 7 months without rest. This is not a new spacecraft. This is not a product of modern technology. It was built before the internet existed, before home computers existed, before most of the engineers now sending commands to it were even born. It operates on about 220 watts of electricity. To put that in perspective, its transmitter is only as powerful as a refrigerator light bulb. And this ancient little underpowered machine that was only supposed to work for 4 years is now sending us information about a region of space that humanity has never had eyes to look into from the inside. The researchers reading its data are not using words like interesting or surprising. They are using words like persistent, unexplained, and our models were missing something. This is the story of Voyager 1. And this is the part the headlines do not tell you. It is not only what Voyager 1 has discovered out there that should make you stop and reflect. It is what is happening to it right now that no one is talking about. It is the story of a scientific question that has been hanging for 5 years that no physicist on Earth has been able to answer, and the window to find the answer is closing year by year, watt by watt, ear by ear that is shut off, and that is what will happen in the next few months. A day locked into the calendar, calculated down to the second, will mark the moment that no human civilization has ever reached before. Stay with me, because by the time this story ends, you will never look at those 3 little ears the same way again. Subscribe right now if you want to hear more stories like this, because we are only just beginning. Voyager 1 crossed the outermost boundary of the solar system on the night of August 25, 2012. But NASA did not announce it to the public until September 12, 2013, more than a year of silence. More than a year during which the operations team knew a historic event had occurred but chose not to say so. Why? The answer lies in the way science itself works. The 2 pieces of evidence on the night of August 25th, the solar particle stream dropping almost vertically, the galactic cosmic ray stream surging upward, met the criteria but were not enough. Voyager might have drifted into a local pocket where the solar wind temporarily weakened while the craft was still inside the protective bubble. This was not excessive caution. Even in 2012, there had already been 3 such temporary crossings in May, July, and August. Each time the charts dropped, the science team held its breath and waited, then the signal returned to normal levels after a few hours or a few days. The night of August 25th could not be allowed to be another thought so but was not moment. A 3rd piece of evidence was needed, coming from an entirely different kind of instrument. And to understand where that 3rd piece of evidence came from, you need to understand the 3 ears of the spacecraft. Voyager 1 carried 10 scientific instruments when it launched in 1977, but only 3 of them could hear the interstellar boundary. The first ear is LICP, the very instrument that counted the drop in the solar particle stream, designed by Tom Crimigas at Johns Hopkins University. The second ear is CRS, Cosmic Ray Subsystem, the instrument that counted the surge in galactic cosmic rays, led by Ed Stone at the California Institute of Technology. Ed Stone himself had been the chief scientist of the entire Voyager mission since 1972, 5 years before the craft was launched. And the third ear is PWS, Plasma Wave Subsystem, designed by Donald Gurnett's team at the University of Iowa. Unlike the other 2 ears that count individual particles, PWS measures electrical oscillations in the plasma through 2 10-meter antennas that spread out behind the craft like rabbit ears. The 3rd piece of evidence had to come from PWS. But the plasma around Voyager was too sparse for PWS to measure directly right away. It needed a shock from the sun, a coronal mass ejection, to excite the plasma into oscillating at its own frequency. From that frequency, Gurnett could work backward to calculate the electron density. There was no shortcut. They had to wait. The necessary eruption arrived at the end of 2012. Its waves traveled 8 months through space and finally reached Voyager 1 in April 2013. PWS recorded oscillations at a frequency of 2.6 kilohertz. Gurnett calculated the electron density was about 0.08 particles per cubic centimeter, 40 times higher than inside the solar bubble, exactly within the theoretical range predicted for the interstellar environment. The 3rd piece of evidence was in hand. On September 12, 2013, at NASA headquarters in Washington, the 600th Ed Stone stood at the podium and announced that Voyager 1 had become the first human-made object to enter interstellar space. But he was careful with his words. He did not use the phrase left the solar system because the solar system still extends to the Oort cloud. He only said it had entered interstellar space. That was the precision of a scientist who had waited 13 months to say one sentence correctly. But that year of silence had its price. In the years that followed, Voyager 1 continued to send data, the 3 ears continued to listen, And what they heard on the other side of the boundary was not entirely what the models had predicted. The first thing that left the scientists puzzled arrived on November 5th, 2018. That was the day Voyager 2, the twin craft, finally crossed the Heliopause, but it crossed 6 years and 2 months after Voyager 1. No model explained that time gap. The Heliopause does not sit still like a static wall. It moves, it expands and contracts, it changes shape far faster than predicted, and when the scientists stitched together the data from the two craft, they reconstructed an unexpected shape. The heliosphere is not a symmetrical sphere. One side curves round like the front of a dome, the other side stretches out behind into a long tail whose exact end no one yet knows. The protective bubble that shields us has the shape of a falling water drop, not a ball. But the most surprising part did not come from the shape. It came from the whisper inside. In the middle of 2017, a doctoral researcher at Cornell University named Stella Koch-Auker began re-examining the entire PWS dataset. She looked for the small signals that the big jolts from the sun had masked. After many months, she found something. A narrow band at a frequency of 3 kilohertz, with a bandwidth of only 40 hertz. Extremely weak, just above the instrument's sensitivity threshold. Not a temporary shock. It was continuous. It was persistent. It had been there since the middle of 2017 and has continued to this day. On May 10, 2021, Auker, together with James Corditz at Cornell and Don Gurnett at Iowa, published the discovery in the journal Nature Astronomy. They offered two possible explanations. The first explanation: this is thermally excited plasma oscillation, particles in the interstellar medium colliding thermally with each other and producing oscillations at their natural frequency. The second explanation: this is quasi-thermal noise, the craft's own antennas interacting with the surrounding plasma and producing a signal that contains information about density and temperature. Both fit within current physics. There is no new physics. But distinguishing between the two mechanisms is an extremely important question. If it is thermal oscillation, the interstellar environment is much warmer and more complex than predicted. If it is quasi-thermal noise, we have a new tool for continuously measuring interstellar density, and many maps of the galaxy need to be redrawn. In the conclusion, Auker wrote that distinguishing the two mechanisms would require either more data from Voyager 1 itself, or a new mission specially designed for the purpose. That question has been hanging since May 2021. To this day, it is still hanging. But this is the part that makes it no longer abstract and turns it personal. Because the heliosphere bubble that Voyager 1 has just crossed is not only a scientific concept, it is a real shield. It deflects the most dangerous forms of cosmic radiation, the high-energy particles streaming out from supernova explosions thousands of light-years away, from reaching the inner solar system at full strength. Without that bubble, the biology that evolved on this planet would be different. There might not be us here to ask the questions, but I need to stop and say something straight to you. This is not a fear-bait story. It is not the kind of Voyager's discovery shows that life on Earth is under threat. There is no scientific evidence for that. There is no peer-reviewed study connecting the 3 kilohertz whisper that Auker discovered to any danger for Earth biology on any human timescale. Anyone who says otherwise is exaggerating for views. What is truly worth reflecting on is much more subtle. We are a species that has telescopes that can see billions of light-years away and mathematical models that describe the inside of a black hole. But we have exactly one witness measuring the interstellar environment directly. Exactly one. And that witness is running out. This is the limit of the species' knowledge, not a biological threat. This is the story of a window that is closing, not a dangerous door that is opening. Every month Voyager 1 can still listen is a month we have the only data in human history. Data that no telescope, no satellite, no Mars mission can replace. Because there are questions about the universe that can only be answered from inside the region of space where the question is asked. And every month Voyager shuts off another sense is a question that is closed, not postponed. Closed, possibly for many generations, because there is no second witness flying out to take its place. And now the story becomes sadder, because before talking about what Voyager will lose in the next few months, we need to talk about what has already been lost in the past 4 years. Because Voyager 1 almost died 3 times in that short period. The first time came in the middle of 2022. Voyager 1 suddenly began sending Earth meaningless telemetry data from the antenna pointing control system, the system whose job is to keep the craft's high-gain antenna always pointed at Earth. For 4 months, the JPL engineers could not understand the problem. The strangest thing was that the craft itself raised no alarm. It did not trigger safe mode. It thought it was operating completely normally, while the engineers on Earth read the telemetry and could not understand who was talking to them. Eventually, they discovered the truth. For reasons unknown, Voyager 1 had switched to using an old attitude control computer that had long been broken. No clear reason, no identified cause, just a strange decision that the 45-year-old craft made on its own in the interstellar darkness. The final fix command was fairly simple: tell the craft to switch back to the correct computer. Fixed. But that problem was only the overture. On November 14, 2023, Voyager 1 suddenly began sending back meaningless strings of binary. Not silence, the signal still arrived regularly through the Deep Space Network. But it could not be read. For 5 months, the JPL team could not decode a single byte. Eventually they found the cause, and it was brutal. A physical memory chip in the flight data system had failed, a memory chip that had been operating non-stop for 46 years under cosmic radiation. The engineers could not repair the chip. It is 24 billion kilometers away. There is no way to touch it by any form of transportation humanity knows. On April 18, 2024, the JPL team sent the solution, not to fix the chip, but to relocate the code to other parts of the memory, split the code into small pieces, test each piece separately, reassemble it. One journalist described it most accurately: brain surgery across a 44-hour communication delay. 2 days after the command was sent, Voyager 1 responded with readable data. The repair was completed in June 2024. Exactly 3 days after Voyager 1 first responded with clean data again, on June 9, 2024, Ed Stone died at the age of 88. He had been the chief scientist of the entire Voyager mission since 1972, 5 years before the craft was launched. 52 consecutive years. No one had ever held the role of chief scientist of a NASA mission for that long. He did not live to see Voyager 1 respond with clean data again. 8 months later, on February 25, 2025, the JPL team sent the command to shut off CRS on Voyager 1, Cosmic Ray Subsystem. The instrument Ed Stone had led for 50 years, the instrument that had counted the surge of galactic cosmic rays on the night of August 25, 2012, now it is silent. It is not broken. It still works normally. It was shut off because there is not enough power. Ed Stone was not the one who made the final decision. He had died 8 months earlier. But if he were still alive, he would probably have been the first to say, "Turn it off," to keep the others running longer. And then 14 months after CRS fell silent, it was the turn of the first ear. 2:16 in the morning Pacific time on April 17, 2026. The exact moment with which we open this story. The engineer in the Pasadena room typed the final command. That command traveled nearly 23 light hours through the void, arrived, and shut LACP off forever. It was not broken either. It was still operating completely normally. It too was shut off because there was not enough power. The JPL team had deliberated a long time before choosing LACP as the next instrument after CRS. The paradox is that LACP itself was more capable than CRS. It could rotate its own antennas and measure many different kinds of charged particles, but that very capability made it consume more power. And the game of counting down every watt capability became a burden. LACP was designed by Tom Krimigas at the Applied Physics Laboratory of Johns Hopkins University in the state of Maryland. Krimigas had devoted more than 50 years of his career to this instrument. He is still alive. He received notice from JPL before the command was sent. There was no ceremony, only a polite phone call and a confirming email. But this was not the first time Voyager 1 lost a sense. On February 14, 1990, Voyager 1 turned its cameras around one last time to take a series of photographs called the Family Portrait of the Solar System. One of those images captured Earth from a distance of 6 billion kilometers. In the picture, Earth was only a faint speck, occupying exactly 0.12 pixels, almost swallowed by a ray of sunlight scattered through the lens. That photograph was named The Pale Blue Dot by Carl Sagan. 34 minutes after the final image of that series was taken, both cameras on Voyager 1 were shut off permanently. The camera system alone consumed more than 40 watts of power, too expensive once the craft was heading into darkness where there was nothing left to photograph. Voyager 1 has been blind since that night, and the list of lost senses continues. In 2006, the ultraviolet spectrometer was shut off. In 2007, the plasma science instrument truly failed from a technical fault that could not be repaired. In 2008, planetary radio astronomy fell silent. During the 90s and 2000s, the infrared spectrometer and photopolarimeter were successively cut to save power. On February 25, 2025, CRS, and now on April 17, 2026, LACP. 7 of the original 10 scientific instruments have fallen silent. The machine has lost sense after sense over the course of 36 years. And there is one detail in that history that will slip past if you do not pause. LACP itself, the first ear, the instrument that counted the drop in the solar particle stream on the night of August 25, 2012, was one of the last ears to be shut off. It had listened to the historic moment it was born to hear. Now it has stopped listening. There is no greater irony in the history of cosmic exploration. After 2:16 in the morning on April 17, 2026, Voyager 1 has only 2 scientific instruments still operating. Those are MAG, which measures the magnetic field around the craft, and PWS. PWS is the final witness among the 3 ears. It is the instrument still sending Earth the data that one day may answer the question Stella Ocker posed 5 years ago, if it lasts long enough before the window closes. But this is something very few people outside the Voyager team know. Because at the same time CRS and LIF were being shut off over the past 2 years, the JPL team has been preparing something they call internally the Big Bang procedure. The name sounds dramatic, but the idea is quite concrete. On Voyager 1, there are electronic components running at lower efficiency than their design capability. There are parts of the electrical system that can be reconfigured, not a hardware upgrade, simply adjusting the way power is distributed inside to extract an extra 4 watts, 6 watts, possibly 10 watts. In the game of counting down every watt, 10 watts is a vast distance. If the procedure succeeds, the team could buy an extra 1 to 2 years of operation for the remaining instruments. In the most miraculous case, they might even turn LECP back on. But the risk is high. Voyager 1 is a 49-year-old machine built before personal computers existed. No one still living has direct experience with the original design of some systems on the craft. The first engineers retired in the 90s, many have died. There are circuits on Voyager 1 that the current team understands only through documentation written in the technical style of the 70s, digitized from thick paper volumes archived at JPL. Changing the power distribution on a system like that can produce unforeseen effects. One wrong command could permanently shut off an instrument with no way to recover. So the JPL team devised the most careful plan possible. They decided to try the Big Bang procedure first on Voyager 2. The twin craft has a little more power in reserve and is closer to Earth, so the signal delay is smaller. Each test command gets a response about 3 hours faster than on Voyager 1. More important, if it fails on Voyager 2, the consequences are less severe. Voyager 2 is not the only craft listening to Ocker's question. The tests on Voyager 2 took place in May and June of 2026. If the results show the procedure is safe and effective, the same approach will be applied to Voyager 1 as early as July of the same year. At the moment you are hearing this story, the JPL team is sitting in that room in Pasadena, analyzing the Voyager 2 test results and weighing the risks for Voyager 1. No one outside the team knows exactly what the outcome will be. No one knows whether LECP will be turned back on. But one thing is certain, whatever the result, this is only buying time. Only buying 1 or 2 more years, possibly 3 if lucky. It cannot buy infinite time, because 4 watts continue to disappear every year, and one day in the 2030s there will be nothing left to reconfigure. To understand why the JPL team dares not rush, we need to pause and look at the power numbers themselves that are counting down. Voyager 1 runs on 3 devices called radioisotope thermoelectric generators, abbreviated RTG. They contain plutonium-238 that decays slowly and converts the heat from that decay into electricity. The half-life of plutonium-238 is 87.7 years. When launched in 1977, the 3 RTGs together produced about 470 watts of electricity. 470 watts for the entire craft, cameras, antennas, 10 scientific instruments, attitude control system, radio transmitter heaters to fight interstellar temperatures near absolute zero. By the middle of 2026, total power is down to about 220 watts, losing about 4 watts each year. 4 watts sounds small, but 4 watts is an LED desk lamp. 4 watts is the difference between turning on or shutting off an ear that has listened to interstellar space for 48 years. The craft's high-gain antenna, the parabolic dish used to communicate with Earth, is 3.7 meters in diameter. The transmitter mounted behind that dish is only 22.4 watts, exactly the power of a refrigerator light bulb. When that 22-watt signal reaches Earth after 23 hours of travel through the void, its remaining power is only 10 to the minus 16 watts, 20 billion times weaker than the power of a wristwatch. The current data rate is 160 bits per second, slower than a dial-up modem from 1981. So slow that if you wanted to download a 5 megabyte JPEG image over this link, you would need about 8.5 years of continuous transmission without pause. To hear a signal that weak, NASA operates the Deep Space Network, 3 complexes of giant antennas placed exactly 120 degrees of longitude apart on Earth's surface Goldstone in California, Madrid, and Spain, Canberra, in Australia. The 3 stations take turns so that Voyager 1 always has some antenna pointed toward it as Earth rotates, but there is a detail rarely told. The DSS-43 antenna at Canberra is the only antenna on the entire planet that can send commands to Voyager 1. Because the craft's trajectory points toward the southern celestial hemisphere, only a southern hemisphere antenna can see it at a favorable angle. Goldstone in Madrid can only receive the signal. If DSS-43 fails, no one on this planet can talk to Voyager 1 anymore. This is a form of scientific patience that very few professions on Earth have ever had to practice. Every question, every hypothesis, every test command must wait tens of hours for a response. The Voyager team has done this for 49 years, and every year the waiting time grows longer. And now we reach the moment on the calendar, the moment that has been locked in. On November 18th, 2026, at 2:16 and 12 seconds in the morning Pacific time, Voyager 1 will reach a distance exactly equal to one light day from Earth. Not a metaphor, a measurement. From that moment onward, every radio signal sent from Earth to the craft will take exactly 24 hours to arrive. No human-made object has ever been that far from Earth in the entire history of human civilization, not in the history of space. In the history of the entire civilization, from the time the first humans carved marks on a bone 30,000 years ago, here is the concrete scenario of what that means. If you are at JPL and send a command on Monday morning, that command travels 24 hours and reaches Voyager 1 on Tuesday morning. If the craft responds immediately, that response travels another 24 hours and arrives back on Earth on Wednesday morning, 2 full days just to complete one communication loop. Every question is 2 days. Every hypothesis that needs testing is 2 days. Every command in the Big Bang procedure is 2 days. The JPL team has lived in that 2-day rhythm for 49 years. Now it reaches the point of a full, exact 24 hours in each direction. On the night of November 18th, 2026, while most of you are asleep, the DSS-43 antenna at Canberra may be sending a command to Voyager 1. There will be no celebration, no live television speech, only a chart on a JPL screen showing that the distance has passed a milestone no machine has ever crossed. Meanwhile, behind the craft, PWS still spreads its 2 10-meter antennas into the void, continuing to record the 3-kilohertz whisper, every second a little more data. Every bit of data, a point on an interstellar map that humanity has never had. The final ear at an unprecedented distance continues to listen. In popular culture, when people tell the Voyager story, they almost always focus on one detail, the golden record. The gold disc attached to the side of the craft, carrying greetings in 55 languages, the laughter of children, the sound of ocean waves, 90 minutes of music from cultures all across humanity, mathematical diagrams and pulsar maps pointing the way back to Earth for anyone who might find it. The golden record was designed by a committee chaired by Carl Sagan. In 1978, Sagan and his colleagues published the book Murmurs of Earth, the Voyager Interstellar Record, describing in detail the process of choosing each piece of music, each greeting, each photograph. That is the beautiful story of what is flying outward. That gold disc was designed to last for billions of years. It may still be intact when the sun becomes a red giant, but there is another story that is almost never told. While Voyager 1 and its golden record continue flying farther out there, is another legacy of the mission that remains here on Earth. That is the data archive. Over 49 years, the 3 years of Voyager 1 have sent Earth an enormous volume of data. Every bit passed through the Deep Space Network was processed at JPL Pasadena, then distributed to the specialized laboratories. PWS data went to the University of Iowa, where Donald Gurnett's group has worked with that same data set since 1977, year after year, without rest. LCP data went to Johns Hopkins. CRS data went to Caltech. MAG data went to Goddard. Ultimately, everything converges in one place, the Planetary Data System, abbreviated PDS, NASA's official archive for all scientific data from space missions. In the very Nature Astronomy paper of 2021 in the Data Availability section at the end, Ocker explicitly notes that the entire dataset she used is archived at PDS with a specific DOI code. A parallel archive maintained by the Radio and Plasma Wave Group at Iowa is publicly available on the internet. That means any scientist anywhere in the world today or 500 years from now can download the exact same dataset Ocker used to discover the 3-kilohertz whisper, can reanalyze it, can run algorithms that did not exist in 2021, can find patterns she missed. This is the core difference between the two legacies. The golden record is a message sent to extraterrestrial beings we may never meet. The PDS archive is a message sent to our own descendants, to scientists not yet born, to questions not yet asked, to algorithms not yet invented. When Voyager 1 finally falls silent someday in the 2030s, this body of data will still be intact. It will not fly away, it will wait. Now let us return to the central question Ocker posed in May of 2021, the question the Nature Astronomy paper left open, the 3-kilohertz signal that PWS has been hearing for nearly a decade, thermally excited plasma oscillation, or quasi-thermal noise. In principle, the answer can come from 2 sources. The first source is Voyager 1 itself. If PWS continues collecting data long enough across different interstellar environmental conditions, the patterns of change in the signal will reveal which mechanism fits better. But Voyager 1 is losing 4 watts each year. Even if the Big Bang procedure succeeds and the JPL team buys an extra 1 or 2 years by the early 2030s, total power will drop below the minimum operating threshold. At that point, no instrument will be able to run. PWS will be shut off. The question will not yet have an answer from the very witness that posed it. The second source is a new interstellar mission designed specifically with modern instruments to measure both quantities simultaneously. The problem is that no such mission exists. The program called Interstellar Probe of NASA and the Johns Hopkins Applied Physics Laboratory in the middle of 2026 is still in the concept study phase. If the United States Congress funds it in 2030, the earliest launch date is 2036. Traveling twice as fast as Voyager, the craft would reach the Heliopause boundary around 2060, 34 years from now. Another generation. If you are hearing this story at the age of 40, you may not still be alive when the successor craft arrives. You may have to hand Auker's question to the next generation, to your children, to your grandchildren, to the scientists not yet born today. The interstellar plasma density map that PWS is drawing, the first continuous map in human history spanning 10 astronomical units with an average sampling interval of 0.03 astronomical units, will stop exactly where Voyager 1 falls silent. After that, a long silence. No one will continue the map. This is not a tragic ending. This is the nature of interstellar discovery, narrow windows, long waits, questions passed from generation to generation, with no guarantee which generation will be the one that finds the answer. This is what I want you to keep from everything you have just heard. The Voyager story is not the story of a machine that is dying. It is far more subtle than that. It is the story of the limits of scientific patience. Of the fact that there are questions about the universe that can only be answered from inside the very space in which the question is asked. Not from telescopes, not from mathematical models, not from satellites around Earth or probes on Mars, only from a machine that has flown far enough to stand inside the region it is describing. And we have exactly one such witness, a witness that is running out before the answer is extracted. Ed Stone died on June 9, 2024, at the age of 88. Before he died, he once said a sentence I want to translate for you. When I look back, I realize how little we knew about the solar system before Voyager. We discovered things we did not know were there to be discovered, time after time. On the night of August 25, 2012, the first ear heard the door open. Today, that ear has closed its own door. On April 17, 2026, in that room in Pasadena, no one applauded, only a brief silence before everyone returned to other work. Because they know what is waiting. Voyager 1 is still sending a signal. At the very moment you hear this sentence, PWS behind the craft is still spreading its two 10-meter antennas into the void, recording electrical oscillations in the surrounding plasma, encoding them into a stream of bits, and sending them back to Earth across a distance of nearly one light day. Of the 3 ears that once heard the door open on the night of August 25, 2012, only one ear is still listening. One machine, 220 watts, one question left hanging, one window closing. The question is whether anyone is listening. If this story is the kind of content you come to this channel to hear, please subscribe right now and turn on notifications. Leave a comment with what made you think the most in this episode, and if you know someone who needs to hear the story of a 220-watt machine sending humanity's final message from the void between the stars, please share this episode with them. Because this story deserves more than the silence it is receiving.